In this video, we're going to define monoprotic and polyprotic acids and bases, and then we're going to go over the steps to writing chemical reactions for polyprotic species that are undergoing a titration. So to start off with, we've got monoprotic acids. So if we break this word down, mono just means one, protic means an H+ ion, so a proton. So paired with the word acid, what this means is that since acids donate their hydrogens or donate their protons, what this means altogether is a monoprotic acid is a substance that can donate only one proton. So some examples of monoprotic acids are going to be substances like hydrochloric acid. So I'm just underlining the acidic hydrogen here. This would be nitric acid, hydrobromic acid, and then we have acetic acid. Now for polyprotic acids, so you're going to need to know the definitions of monoprotic acids, polyprotic acids, monoprotic bases, and polyprotic bases. So if we break down the words polyprotic acids the same way that we did for monoprotic acids, poly just means two or more. Protic means proton. And acid means that we're donating the protons. So altogether, a polyprotic acid is a substance that can donate two or more protons to some other substance. Now, the words polyprotic acid, that's a general word, so it's kind of like a big umbrella, and there's a couple of smaller terms underneath this umbrella that specify just how many protons can be donated. So for example, a diprotic acid can donate 2 protons to a base, because di means 2, and then a triprotic acid can donate 3 protons to a base. So for example, we have sulfuric acid. So here's our acidic hydrogens. So this would be a diprotic acid. Over here we have phosphoric acid. So this would be a triprotic acid. The next species is dihydrogen phosphate. So this is an ion, but if we are talking about it acting like an acid, this would be a diprotic acid because it has 2 hydrogens that it can donate. So with specifying what type of acid that you're dealing with, the subscript after the hydrogen, after the acidic hydrogen, I should say, that is going to tell you whether your acid is diprotic or triprotic, or if you're talking about a monoprotic acid, you're only going to have 1 acidic hydrogen. The reason why I'm specifying that the hydrogens have to be acidic is that not all hydrogens are acidic. So for example, in acetic acid, these 3 hydrogens are not acidic. It's only this hydrogen here. Okay, there's a little typo here. I'm just going to make it so that the negative is superscript rather than subscript. And then our last species is oxalic acid. So I'm just highlighting or underlining the acidic hydrogens here. So we have two hydrogens that are acidic, so this is a diprotic acid. Now, moving on to bases. Monoprotic base, what that means, we already know mono just means one, protic means proton, and base means that it's going to accept the protons. So altogether, a monoprotic base is a substance that will accept only one hydrogen. So an example of this would be ammonia. It can accept one hydrogen to become an ammonium ion. Next, we've got polyprotic bases. So these are bases that are going to accept two or more hydrogens. So a diprotic base, or something that's dibasic, can accept two protons, and a triprotic base can accept three protons. Okay, so I'm just going to make some adjustments to our examples here. So the 3- should be superscript because it's the charge. Same with the 2- for the carbonate ion, and the 2- for the hydrogen phosphate ion. Okay, so looking at the three examples that we've been given, how you can figure out whether a base is diprotic or triprotic is typically you just look at the charge. Of course, with chemistry, there are exceptions. So our exception to just being able to look at the charge and being able to tell how many protons a base can accept, the exception would be ammonia. But for other bases, you can just look at the charge. So since this has a 3- charge, it tells you that it can accept 3 hydrogens in order to get to a neutral charge. Okay, so I'm just going to write what I said. We'll have to squeeze it up here. The negative charge tells you how many protons a base can accept and of course we have to list at least one exception, but the most notable exception would be ammonia. So you just have to know that ammonia can accept one hydrogen. Okay, so again, with bases, look at the charge to tell you how many protons a base can accept, with the exception being ammonia. Whereas for acids, look at how many acidic hydrogens are contained within the chemical formula for that acid. So acidic hydrogens, they are going to occur either at the very beginning of the chemical formula or at the end of COOH. Those are where your acidic hydrogens are going to be for acids. Okay, going back to our bases, since this carbonate ion has a 2- charge, that means it can accept 2 protons in order to get to a neutral charge. So that means that this is going to be a diprotic base. And for hydrogen phosphate, because it has that 2- charge, that is also going to be a diprotic base. Now, as we've discussed, some substances can be amphiprotic. They can act as acids or bases. So with hydrogen phosphate, yes, it is a diprotic base. However, since it does have one hydrogen, it could act as a monoprotic acid, although it's not incredibly likely that that would happen. Okay, if we look at the dihydrogen phosphate ion, yes, it is a diprotic acid because it has two acidic hydrogens. However, because it has this -1 charge, that means it could also act as a base and it could accept one hydrogen. So this would be a monoprotic base. Okay, so some substances can have more than one label to it. Typically, questions are going to specify whether amphiprotic substances are acting as an acid or a base, so you shouldn't have to guess at that. Now, with polyprotic bases, they can react more than once with an acid. So for here, we do have to make some adjustments, just some superscript charges here. So I'm going to go through that really quickly. So here we have our phosphate ion, so PO4 with a 3- charge. It's reacting with water, and water is donating a proton to the phosphate ion. So then we get hydrogen phosphate, so HPO4 with a 2- charge, and hydroxide for our products. For the subsequent reactions, we're going to take the conjugate acid of this base and we're going to keep on reacting it with water in order to see how the subsequent reactions happen. Okay, so in other words, choose the ion that is not hydroxide. So with HPO4 2- reacting with water, again, water is donating a proton because the whole point of this section is just to show all of the reactions that can happen when you start with a phosphate ion. Okay, so hydrogen or a proton gets donated to hydrogen phosphate, and we get H2PO4 1-. Okay, so we're going to take this ion and keep reacting it with water to show the last reaction where we have a neutral compound. Okay, so we have dihydrogen phosphate reacts with water, water donates a proton, and we get H3PO4, which is phosphoric acid, and a hydroxide ion. Okay, so the goal with this would be to take the phosphate ion and react it with water, and each time you're only transferring one hydrogen or one proton at a time. So where this is going to apply is when we have a polyprotic substance, whether it's an acid or a base, undergoing a titration where either an acid or a base is continually added. There may be more than one Bronsted-Lowry reaction taking place. So this is going to happen with either polyprotic acids or polyprotic bases in titrations. So the steps for how you would write these reactions that are happening throughout a titration are as follows. So you're going to write the quantitative Bronsted-Lowry reactions. Now you're going to be told how many of these reactions that you need to write. And you're going to be told this usually in the form of how many endpoints there are in the titration. Okay, so each endpoint is going to be a quantitative reaction. Remember that quantitative reactions have these forward arrows or these single-headed arrows in them. They are not the ones, these are equilibrium arrows. This is a quantitative reaction. Now, if the product in the last reaction has a hydrogen either to accept or donate, so whether it accepts or donates just depends on if it's a base or an acid, because remember, bases accept hydrogens or they accept protons, and acids donate protons. So if the product in the last reaction has another hydrogen to accept or donate, then you need to write an equilibrium reaction as well. Okay, and then for the last reaction, you're going to write a net reaction that combines all of the quantitative reactions. So it's only the quantitative reactions that you're combining. You do not include the equilibrium reaction, only the quantitative. Okay, and I just want to add in here for the second point, you only consider writing an equilibrium reaction once you're finished your quantitative reactions. Okay, so let's try this out in an example. So we have sodium hydroxide. We have a sodium hydroxide solution that is continuously added in a titration to phosphoric acid until the second endpoint is reached. Using phenolphthalein as the indicator, write all of the quantitative and equilibrium reactions for this process, including the net reaction. Okay, so to get questions like this started, it's going to start off extremely similar to what we did on page 46. So I'm just going to show you that really quick. So here where we started off with a species list and then we identified our strongest acid and our strongest base based off of their positions in our data booklet on page 8 and 9. We're going to be doing exactly that. So let's get that started here. So step 1, species list. Okay, so we're given a sodium hydroxide solution. So sodium hydroxide, if we look at our solubility table, so hydroxide is right here, and it says with group 1 ions, which sodium is. So if you look at your periodic table, I've already got sodium circled on the far left here, so it is part of group 1, or it's in the first column. So because hydroxide, when it's paired with any group 1 ion, so including sodium, that's going to be very soluble. So that means that this ionic compound is going to dissociate. So what that means is sodium hydroxide, since it's a solution, I'm going to say aqueous, breaks apart, into its cations and anions. So these products we are going to have in our species list. Now, since it says that we have a solution, that means that water is going to be present, because solution means that your substance is dissolved in water. So we're going to write water as a liquid here, and then we have phosphoric acid. So with phosphoric acid, going to page 8, we just need to double check to make sure it's not one of our strong acids. So phosphoric acid is not in our list of strong acids, therefore it's going to be a weak acid. The reason why this is important is because strong acid, the quickest reaction that happens when you have a strong acid present is the strong acid reacting with water to produce hydronium and whatever conjugate base is left over there. Okay, so just keep that in mind. If you get a titration question where a strong acid is used in your species list, you would have to list the products of the strong acid reacting with water in your species list. So that would be hydronium and the conjugate base of the strong acid. Okay, but because phosphoric acid is weak, we can just list phosphoric acid. I don't need to worry about listing hydronium. And acids are always aqueous. Okay, so with this species list, what we're going to do is I'm going to go through my table on page 8 and 9, and I'm going to circle these species in my list just so that I can see where they are in relation to each other. Now, before I get there, sodium, any metal ion, is going to be neutral. You're not going to find it on page 8 and 9 of your data booklet, so don't even worry about sodium. It's a spectator ion. It's not going to take part in the reaction. So I'm just going to cross that off right off the get-go, and then we'll worry about the rest of these. Okay, so I know I had water in there, and water appears 2 places, and I know I had hydroxide, which is there, and then we had phosphoric acid, so I need to find that there. There. Okay, so for your own data booklet, you could either lightly circle these in pencil, or you could use one of those small sticky note tabs just to mark the places of all of your substances in your species list, because otherwise your data booklet gets pretty rough and ragged looking there. All right, so now we need to pick our strongest acid and our strongest base. For the strongest acid, I'm going to put my finger at the top of the acid formula column and then trace my finger down until I hit my first acid. So phosphoric acid, out of the species list that I have, is the strongest acid. So I'm going to label that. Strongest acid. And now we need to determine our strongest base. So to determine the strongest base, you start in the bottom right-hand corner, so right here, and then you typically trace your finger up. I should erase this because that wasn't in our list. But you typically trace your finger up, and whatever you run into first is going to be your strongest base. But since we're starting right at hydroxide, we can say that hydroxide is our strongest base. So we already did step 2 here. I just want to write it out. Step 2, choose your strongest acid and strongest base on page 8 and 9 of your data booklet. All right, so that's already done, so I'm going to move on to step 3, which is when we're going to start writing our quantitative reactions. So the quantitative reactions are only going to involve our strongest acid and our strongest base. So after we're done writing our quantitative reactions, if applicable, which it is in this case because it does, the question does say, write all of the quantitative and equilibrium reactions for this process. So after we're done writing the quantitative reactions, we will have to write an equilibrium reaction. But what I'm going to do is I'm just going to make this general enough to apply to a wide range of questions. Okay, so for our first quantitative reaction, so again, we have hydroxide ions reacting with our triprotic acid, phosphoric acid. Okay, now sodium hydroxide is constantly or continuously being added to phosphoric acid. Okay, so what this means is we're going to write 2 quantitative reactions. How we know we're only writing 2 is because the question says that the titration only goes to the second endpoint. So that means we only need to write 2 quantitative reactions. Okay, so these reactions are going to show phosphoric acid losing 2 hydrogens, but it's going to happen only one at a time. So whenever you're writing reactions for like acid-base reactions, you're only ever transferring 1 hydrogen at a time. Do not transfer more than 1. So we have phosphoric acid reacts with hydroxide. So our acids, remember A for away. So 1 hydrogen is being transferred away. And since they're quantitative reactions, we're going to use this arrow. We're not going to use the equilibrium arrow. So then I'm going to imagine my acid just with 1 less hydrogen to it. So H2PO4. and the charge for that is going to be 1 minus. So you can either double check the charge in your list of polyatomic ions, or you could just say, well, this phosphoric acid started out as a neutral charge. We lost a proton, so 0 minus 1, that's how we're getting negative 1. Okay, now for our other product, we need to imagine the hydroxide ions just with one more proton in it, so that would be water. And water is always liquid, it is never aqueous. Okay, for the following reaction, what I'm going to do is I'm going to keep on reacting the conjugate base to my acid to show that it loses another hydrogen there. And because sodium hydroxide is being continuously added, I react it with the hydroxide ions because that is my strongest base. So essentially, for the first quantitative reaction, we were reacting our strongest acid, phosphoric acid, with our strongest base, which is hydroxide. Okay, for the next quantitative reaction, we are going to react our next strongest acid, which is the dihydrogen phosphate. So you'll always be able to find either your next strongest acid or base in the products of your previous quantitative reaction. So again, we're treating this like an acid, even though technically it's a diprotic acid, but it could also be considered a monoprotic base. However, for the purposes of this reaction, hydroxide is a much stronger base than this, so that's why it still acts as an acid in this situation. Okay, if you wanted to prove that to yourself, you could find dihydrogen phosphate, so that will be right here. So because this is, even though it's a weak acid, the base is still a lot stronger than this. And if you can draw like a line that, as you read it from left to right, like it looks like a downhill line, then you know that this substance still keeps on acting as an acid because it's reacting with a stronger base. So we're transferring just one proton at a time still. So then for our products, we're imagining our dihydrogen phosphate ion with just one less hydrogen. So now it's just hydrogen phosphate with a 2 minus charge. And then hydroxide with one extra hydrogen, that's still going to be water. Okay, so those are our two quantitative reactions. I'm going to stop there because it says that the titration stopped at the second endpoint. Okay, it didn't continue on to a third endpoint there. So now at this point, we need to write an equilibrium reaction. So what we're doing is we're taking the conjugate base to our acid and we're writing an equilibrium reaction between it and hydroxide. And the reason for that is, again, just because hydroxide's being continuously added, so there's a lot of it around. So because it's an equilibrium reaction, I'm using the equilibrium arrows. Now, again, if we look at our data booklet and we find hydrogen phosphate, we're going to find it right here. So even though it's not much of a downhill line, it still is. So that means even though hydrogen phosphate is a very weak acid, hydroxide ions are still going to be a stronger base than this could ever be. Okay, even though technically you could call it a diprotic base. So because of that, what we're going to do for our equilibrium reaction is we're going to transfer one last proton here, and our products are going to be the phosphate ion and water. So again, we're just imagining hydrogen phosphate with one less hydrogen for our first product, and then we're imagining hydroxide with one more proton to it because we transferred one proton. Okay, so now we need to decide if the forward reaction is favored versus the reverse reaction. So looking back at our data booklet, because we have a line that, like, it looks like it could be a downhill line, okay, as you read it from left to right, what that means is since our base is below our acid, the favored reaction is going to be the forward reaction. So that's only going to occur if the base is below the acid. If it was the other way around, then we would have to say like that the backwards reaction is favored. So if the base was above our acid, then we would say the backwards reaction is favored. But in this case, we need to say that the forward reaction is favored because the base is below the acid. So how I'm going to represent that? There's a couple ways to represent that, and we went over that on page 46. But I'm just going to say forward reaction is favored. This is how I'm communicating it. Okay, so now we need to write the net reaction. So remember, for the net reaction, it only focuses on the quantitative reaction. You kind of just ignored the equilibrium, and the equilibrium is not part of the net reaction whatsoever. So with looking at our pink quantitative reactions here, we're going to want to first pick out any substances that appear both on the reactant and product side. So what I'm noticing is we have dihydrogen phosphate here and here. So because there's equal amounts on opposite sides of the reaction arrows, these cancel out completely. Now, there's not any other substances that are on opposite sides of the quantitative reaction arrows for my pink reactions. So what I need to do next is I can move on to writing the reactants for my net reaction. So I am starting with phosphoric acid. Now, between the two quantitative reactions here, in total, I'm using 2 moles of hydroxide ions. So because they are on the same side of the quantitative reaction arrow, so they're both reactants, I'm going to add them up. So I'm going to go 2 hydroxide ions, aqueous, And since we're doing the net reaction of the quantitative reactions, that's why I'm using a quantitative arrow. And then I'm going to move on to the products. So it looks like I have one hydrogen phosphate ion. And then I have 2 moles of water. Now the net reaction is done. Okay, so underneath here it says, let's draw a sketch of what this pH curve would look like for the above titration. So doing a sketch of this, what it's going to look like is this. So right at the steepest points here, the middle of the steepest points I should say, these are going to be our endpoints. So this is the first endpoint. And it's going to be where our first quantitative reaction happens. Up here is going to be our second endpoint, so that's where our second quantitative reaction would occur. And I should be writing second endpoint here. Okay, so let's just identify a couple other pieces that are important for a titration curve. So when you get these plateaus, these are called buffer regions. So essentially buffer regions are where the pH really doesn't change all that much. So this is going to be the first buffer region. This will be the second. Now, you may be thinking, well, this is a plateau, so that should be another buffer region. Your last plateau is never a buffer region because this is where the equilibrium reaction would happen. All right, and that's it.